back. So in the previous lecture, we talked about the pressure gradient force, which is what creates wind. If we didn't have that, we wouldn't have any wind. But once the wind gets started, what affects it? What steers it? What causes cyclones? And so on. Well, to understand wind, we need to understand what wind is. Well, wind is air in motion. And just like all objects in motion, wind follows Newton's laws of motion. Now, I'm sure you've probably heard of Newton's laws at some point in your life, so I'm just going to blitz through them here. The three laws are this. The first law states that an object in motion will stay in motion unless a force acts on it. That's called inertia. The second law is that the force exerted on an object is equal to mass times acceleration. We call this F equals ma. And the third law is that every action has an equal but opposite reaction. We're not going to worry about the third law in today's lecture. We're just going to focus on the first two laws. So, using these first two laws, we see that assuming that the mass of the atmosphere stays constant, forces acting on it accelerate it. And this is what creates wind. So if we assume that the mass of the atmosphere stays constant, force is proportional to acceleration. Therefore, forces accelerate the wind. Now, what does acceleration actually mean? Well, it can mean one of three things. It can mean speeding up the wind, which we talked about in the last lecture. It can also mean slowing down the wind, and it can also mean steering the wind. So forces either speed up the wind, slow down the wind, or steer the wind. Now, there are four main forces that act on the wind. For the purpose of this class, we're really only going to talk about three, though. The forces are the pressure gradient force, which we've already talked about, that speeds up the wind. The Coriolis force, which steers the wind. The centripetal force, which has to do with the curvature of the wind. And friction, which slows the wind down. We're not really going to talk much about this centripetal force. I'm going to mention it for 30 seconds and then we're going to move on. Since we've already talked about the pressure gradient force, today's lecture we're going to focus on the Coriolis force and on friction. So let's talk about the Coriolis force. The Coriolis force is caused by an imbalance caused by the rotation of the Earth. So this is caused by the rotation of the Earth. A good analogy to this is, suppose you and a friend, fed up with this class, decide to go play in a merry-go-round just for fun. And the two of you are tossing a ball between each other. If the merry-go-round is at rest, when you toss the ball from one end to the other, doing so causes the ball to go on a straight path. However, if you were to begin to spin this merry-go-round, the ball will still go on a straight path. However, because you and your partner are going to be moving, that's going to make it seem as the ball has deflected. The ball has actually shifted its course. So it's actually not the ball that's changing position, it's you that's changing position. Since we live on an Earth that rotates, objects that are traveling feel this same deflection. Now, what I really want you to know is this. The Coriolis force takes an object in motion and it steers it to the right of its path in the northern hemisphere and to the left of its path in the southern hemisphere. Now, the confusing thing that a lot of students get caught up with, and what I got caught up with when I was studying this, is they think that when they say to the right, they mean to your right. but it's not to your right. It's to the right that the object is traveling in. So let's say we have an object and it's traveling this way. What direction is the Coriolis force going to turn that object? Well, since the object is traveling down, the right of its path would be this way. So the Coriolis force is going to turn it that way. That's your left. But for the object, it's the object's right. So again, it turns it to the right of the object's path, not to your path. So this merry-go-round analogy kind of helps you understand this. But again, what I really want you to get is Coriolis force steers wind to the right in the northern hemisphere, to the left in the southern hemisphere. And there's a good YouTube video about this, and I'll put this in the comments below at the end of this video. Now, there's also a good video that the textbook has. If you want to check out this video, go to the textbook's website or ask me and I can send you a link to this video. But the previous YouTube video is also good and you don't have to buy the textbook to view it. Now, the consequence of this Coriolis force is when you have wind, such as wind that's approaching the center of a cyclone, this wind is then deflected and it rotates around the cyclone. Now, what determines how strong the Coriolis force is? So in the last lecture, we talked about the pressure gradient force was caused by two things: difference in distance. Well, the Coriolis force is dependent on three things. The three things are the latitude, the speed of the wind, and the size of the motion. So let me take each one of these in sequence. So first, latitude. The reason why we have the Coriolis force to begin with is because of what's called angular momentum. The angular momentum at a particular latitude is different than it is at the equator. It's this difference between the two latitudes that causes the Coriolis force. As a result, the further away you get from the equator, the stronger the Coriolis force becomes. The closer you get to the equator, the weaker it becomes. So, the higher the latitude, the stronger the Coriolis force. The next thing is speed. The faster the object is traveling, the stronger the Coriolis force. So, the analogy I love to give is, let's go back on that merry-go-round, and let's say you lob the ball to your friend. That ball's not going to experience a strong Coriolis force. On the other hand, let's say you like to play your favorite or your best Randy Johnson impersonation. If you've never heard of Randy Johnson, look him up on YouTube. Not for the weak at heart, but he throws, or he used to throw, he's retired now, he used to throw really fast pitches. Well, let's say you decided to do your best Randy Johnson impersonation and you hurl the ball at your friend. The Coriolis force on that ball is going to be greater because the speed is faster. This is one of the reasons why cyclones, such as hurricanes, have very, very tight spirals, because the winds inside these hurricanes are really strong. And then finally, the size of the motion. Now, a lot of people, when they hear the Coriolis effect, and when they hear this, they go, oh, great, so this explains why the water in my toilet bowl swirls. Unfortunately, the water in your toilet bowl is such a small scale that it actually doesn't experience a Coriolis effect. So, sorry, you have to look up something else. Sorry about that. Nope, it's not large enough. Now, So far we've talked about the pressure gradient force and the Coriolis force. Well, in the upper atmosphere, these two forces balance each other out. Here's how this works. Suppose you have a particle of air at rest, and you release it. The pressure gradient force is going to take that particle of air, and it's going to push it from high pressure to low pressure. Now, the pressure gradient force is an acceleration force. So, as the parcel of air is traveling, it's also speeding up. As it speeds up, the Coriolis force strengthens. It becomes stronger and stronger and stronger. That causes this parcel of air, as it approaches the low pressure and speeds up, to begin to turn to the right. Once it turns to the right, it's still speeding up, but eventually it reaches a point where the pressure gradient force has sped it up so much that the Coriolis force has become equal to it. In this case, the two cancel each other out, and this is what's called geostrophic balance. In the upper atmosphere, so this is well above the surface of the Earth, the pressure gradient force and the Coriolis force cancel each other out. And as a result, wind flows parallel to isobars in the upper atmosphere. These are what are called straight-line winds. We're going to talk more about that in a moment. There's another good video from the textbook on geostrophic balance. I legally can't show it here on this YouTube video, so sorry, you're going to have to look it up elsewhere. But if you want to see more illustrations of this, there's some other good videos on YouTube that I'll put in the comments below. Now, the geostrophic balance acts like water in a stream. When the isobars, and remember those are lines of constant pressure, when they're far apart, that means you have a small difference over a large area. Therefore, the wind is going to be very weak. Why? Because the pressure gradient force is going to be very weak. However, if the isobars are very close to each other, just like we talked about in the last lecture, close isobars means strong pressure gradient. In that case, you get strong winds. You get fast-blowing winds. Now, this is all good with straight isobars. The wind just follows in a straight path along these straight isobars. However, in the upper atmosphere, a lot of times these isobars are actually curved. And what that causes is that causes the wind to still flow parallel to them, but to be turning as well. It's forced to change directions. So the wind would be flowing like this. So let me actually draw some curved isobars. So something like this. So here we have two curved isobars. And let me get another color here. I'll use green. The wind is traveling in one direction. Then when it hits those curved isobars, it also changes direction. It curves with those isobars. This is what's called a gradient wind. And the change in direction is called centripetal acceleration, and it produces a force called the centripetal force. That's all you need to know about centripetal force. Centripetal force is always directed into the center of a pressure system. Now, again, we're not going to worry too much about centripetal force. But what I do want you to know is what are called cyclonic and anticyclonic flow. Cyclonic flow is when wind is rotating around a low pressure. In the upper atmosphere, the wind flows parallel to these curved isobars. So it's going to flow like this. It's going to flow parallel to these curved isobars. And despite my poor attempt at, despite my poor attempt at drawing a perfect circle, as you can see, I'm not the greatest artist. Basically what's happening is that as this particle of air is circling the low pressure system, it's not getting closer or farther from it. It's circling it at a distance that doesn't change. That's what happens in the upper atmosphere. Now, cyclonic flow is flow around a low pressure system, and here in the northern hemisphere, it flows counterclockwise. Around a high pressure, wind also rotates around it, but instead of rotating counterclockwise, it rotates clockwise. This is what's called anticyclonic flow. So cyclonic flow is counterclockwise around a low pressure. Anticyclonic flow is clockwise around a high pressure. Now, with all of this said, in the upper level, winds are traveling parallel to isobars. There are two types of winds that we talk about: zonal winds and meridional winds. Winds are zonal when they travel in a straight west to east direction. So this side right here of the United States is experiencing a zonal wind. On the other hand, meridional winds are when winds have a high north-south component. That would be over here. Now, in the upper atmosphere, the pressure gradient force and the Coriolis force balance each other out, and all is well. Not so much near the surface of the Earth. Near the surface of the Earth, we have the effects of buildings, trees, vegetation, you and I, and so on. These create what's called friction. Now, friction is only important in the lowest 1,000 meters of the atmosphere. This is what's called the planetary boundary layer. But friction wreaks havoc on the wind in this lowest 1,000 meters. Now, if you've ever flown on a plane and you felt a smooth flight pretty much all the way throughout the plane, but you begin to notice turbulence as you're approaching the runway, as you're beginning to land, it's likely because your plane has entered the boundary layer. And the boundary layer is much more turbulent than the area above the boundary layer, which is what's called the free atmosphere. Now, friction acts to slow the wind down. Friction acts to slow the wind down. Now, before friction was acting on the wind, the pressure gradient force and the Coriolis force were equal to each other. Hence, the wind was geostrophic. However, when you throw in friction, friction slows the wind down. Which of those two forces, the pressure gradient or the Coriolis force, is going to be affected by this? Well, the answer is the Coriolis force. The Coriolis force is going to be affected by this because the Coriolis force is dependent on the speed of the wind. Pressure gradient force isn't. Pressure gradient force is dependent on difference in distance between high and low pressure, whereas Coriolis force is directly related to the speed of the wind. Now, the way that this works is at the surface of the Earth, so this is not a loft in the atmosphere, this is at the surface, the Coriolis force becomes weak compared to the pressure gradient force. As a result, not only do winds rotate around a pressure system, but they move either out of it if it's high pressure or into it if it's low pressure. And this is because the pressure gradient force is now stronger than the Coriolis force. What I want you to know is that in the northern hemisphere, winds rotate counterclockwise and into low pressure, and clockwise and out of high pressure. Now, it's different in the southern hemisphere. In the southern hemisphere, pressure gradient is still the same. Winds always blow from high to low. But the Coriolis force is the opposite direction in the southern hemisphere. As a result, in the southern hemisphere, winds rotate counterclockwise and out of high pressure, and clockwise and into low pressure. Now, the last thing I'm going to talk about in this lecture and in this module is convergence and divergence. So, convergence occurs near low pressure. Remember, winds blow from high pressure to low pressure. As a result, winds are blowing towards, that means into, low pressure. Once these winds reach the center of the low pressure, they converge. Once they converge, they have nowhere to go but up. This is the reason why low pressure gives us stormy weather. Because in low pressure, you have winds that are converging and they have to rise. So low pressure causes convergence, which causes rising air. This rising air then cools, expands, and condenses, giving us clouds and the weather we all know and love. On the other hand, in the case of high pressure, we have divergence. Air is escaping the high pressure system. In this case, the air is sinking above it because air from above has to fall down to take place of the diverging air. This causes air to be sinking here, and when you have sinking air, you don't get any precipitation. So you get convergence around low pressure, divergence around high pressure. So in this lecture, we talked about the Coriolis force, which steers wind to the right in the northern hemisphere, to the left in the southern hemisphere, and is dependent on the speed of the wind, the latitude, and the scale of the wind. And then we also talked about friction, which is only important in the lowest 1,000 meters. That's what's called the boundary layer. We also talked about geostrophic balance, which happens in the upper atmosphere when the pressure gradient and Coriolis forces cancel each other out. Near the surface of the Earth, friction throws that balance off, and therefore winds rotate into low pressure and out of high pressure. So if you have any questions, please feel free to contact me. Please don't hesitate to ask. That's it for this module. The next module, we're going to talk about measuring wind, and we're also going to talk about global circulation. Until then, I'm Terrence Mullins. Thank you.